All right, we are almost done here, and we have one more talk for you before we get into the cool badge hacking and closing ceremonies. Right here we have Steve Collins. He's a guidance and control engineer at JPL. He was the crew's ACS systems engineer for the Curiosity rover and has worked on numerous missions, including Dawn, Deep Impact, the Mars Exploration Rovers, Deep Space DS-1, and Galileo. In-flight jobs, Steve's jobs consists of keeping spacecraft pointed in the right direction, making trajectory corrections, and figuring what the heck just happened. He flies spacecraft around the solar system as his job. So everyone, please give a warm welcome to Steve Collins here.
Hello, hello, hello. Thank you very much. Thank you very much. Happy to be here. I see a fair number of people I recognize. I see some JPLers. I see some SpaceX people. You guys probably know more about this than I do, but here we go. So yeah, I'm here to talk with you about what we do when things go wrong in space, which they always seem to do. First, let me start with trying to present a little bit of hacker cred. I grew up fooling with a Commodore 64 and, playing with machine language programming got me my first space job because I knew 6502 assembler. This thing that maybe you can sort of resolve is a letter quality printer. It's actually a crazy motion system thing that sits on top of an electric typewriter, and the Commodore 64 could drive it over the keyboard and press keys with it. It printed about one page every 10 minutes or something, but my little I/O board that I built for it is there. So some 3D modeling, early 3D rendering stuff. So this is what I do today. I work on controlling the attitude of this mic boom, which seems to have a little bias. Let's see, there we go. I work at the Jet Propulsion Laboratory. I'm an attitude control engineer, and attitude is the term of art that we use for the orientation of the spacecraft, keeping a spacecraft pointed in the right direction. While someone said this was proof that we have a time machine, you can see in my case that's not really true. So why do things go wrong in space? Well, space is a difficult place. It's a very extreme environment. There's no gravity. You experience large temperature extremes. If you just sit something out in full sun in Earth orbit or at the range from the sun of the Earth, it'll get up to like boiling temperature just sitting out there in the sun. But if you put it in the shade, then it's looking at the cold blackness of space and will get very, 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 very cold. And so when we design spacecraft and components for them, they have to be able to deal with those temperature extremes. They have to be able to survive the launch environment of the rocket. They have to not emit radiation harmful to other parts of the spacecraft, radio waves, and so forth. The spacecraft that we built are typically one-of-a-kind, very specialized designs. It's, in the communication satellite world, sometimes you'll build a whole series of spacecraft that are very much the same. The launch vehicle community builds, several launch vehicles that have small design changes but are largely the same. In deep space exploration, we typically are building spacecraft that are designed for a very specific mission. They're using every bit of their payload capability and every bit of their power capability to run their science instruments and do their science mission. And because of that, they're fussy. And they're, the only spacecraft like that made. It was sort of unusual for JPL to build Spirit and Opportunity and have them be twins. Voyager spacecraft were like that too, where there were two built. So pretty much all of our spacecraft are experimental. They're beta test, one-of-a-kind critters. And spacecraft, because of that, need to be able to take care of themselves when they're out there in the universe. Sometimes it's a very long time between when, the amount of time it takes for us to notice that there's a problem and get some sort of commands up to the spacecraft to help it out can be hours to days in some cases. There's some examples here of the time it takes for light to just get to the moon is a second or two, which makes it hard if you're trying to drive a RC car on the moon with a 1 or 2 second delay. It's pretty hard to do. Mars varies from a few minutes to 20 minutes or something. That's the one-way time. If you see something funky in your telemetry, it's maybe 15 minutes old. And if you did something instantly to respond to that, it'll take 15 minutes for that response to get back up to the spacecraft. Jupiter's even farther, and Pluto farther even than that, where it's hours and hours between getting your telemetry and being able to send a command. And oftentimes the spacecraft is designed to be out of communications, either because it's behind Mars, or it's nighttime on Mars, you're a rover sitting on the surface, or in the case of Dawn or Deep Space One, you're thrusting the spacecraft is using an ion propulsion system to thrust some direction, and needs to be doing that and not pointing its antenna at the Earth. So how do we get spacecraft to take care of themselves? Well, a common way to do that is this thing we call safe mode. It's an operating mode of the flight software that uses a minimum amount of sensors and actuators. It basically, turns off all the science instruments and tries to make the spacecraft use as little resources as it needs. Typically, we switch the communication onto a low-gain antenna, which is sort of an omnidirectional antenna, so that no matter what direction the spacecraft is pointed, we can still have communications with it, get a little bit of telemetry, and send commands to the spacecraft. But typically, if you're on a low-gain antenna, you can only communicate with the spacecraft very slowly. A typical low-gain situation might be 10 bits per second, or even lower than that. And you can type faster than 10 bits per second. A regular high-gain antenna situation might be thousands of bits per second. A spacecraft like MRO that has a great big high-gain antenna on it, has many tens of thousands of bits per second communication rate capable. So the spacecraft, will detect some sort of a fault on board, and it'll go into this safe mode. And typically, once it does that, it takes you a day or two to figure out exactly what went on, because you're trying to do it at a very low telemetry rate. And then once you figured it out, oftentimes you have to, get the spacecraft reconfigured for normal operations again, and that can take several days to accomplish that. So how do we get a spacecraft that we've designed from there's really no fucking way this is going to work to we're pretty sure that this multi-billion-dollar thing that we built is going to safely land on Mars and is really going to work? One of the ways we do that is with hardware redundancy. We put multiple copies of things that are crucial for the spacecraft operation on the spacecraft so that we can switch to them if one of them craps out. We would do that maybe for a star sensor that figures out the spacecraft's orientation in space, or thrusters or gyroscopes and stuff like that. Oftentimes we'll have multiple flight computers that are on there. And in addition to that actual hardware redundancy, we try to have functional redundancy. And that's a situation where you have more than one way to do something. An example of that is a lot of our spacecraft have these devices called reaction wheels on them that control the spacecraft attitude. They're basically a flywheel with a motor on it, and you spin the motor one direction and it makes the spacecraft turn the other direction. We'll have those on a spacecraft, but we'll also have thrusters. And we will typically build the spacecraft so that if we're in safe mode, we use the thrusters to control the attitude of the spacecraft instead of the reaction wheels. So there's multiple ways to control the spacecraft's attitude, and that having those multiple ways means that if there's a specific problem with the reaction wheels, that we're still able to do the mission. Dawn, the Dawn spacecraft, which is in orbit around Ceres, had several failures of their reaction wheels, and it has been operating since the reaction wheel failure, using thrusters and stuff to keep the mission going. Let's see. So how do you know when you're having a problem? Let me just check my time here. It's 4:30, and I'm 6, so I'm going to have to speed up just a little bit. How do we detect it when there's a problem? Well, there's typically a system in the flight software called the fault protection system. And the fault protection system has pieces that are monitors, things that look at pieces of hardware and how the spacecraft is operating and decide if they think if everything is okay. And then in addition to those monitors, we have responses, which are things that they're behaviors that we can trigger if we think something is not working right. For example, if we think there's a problem with a reaction wheel, the first level of response might be to power cycle that thing to see if, it's just a single event upset in its electronics, and sometimes power cycling it will make it come back and operate normally. We will sometimes do a thing that we call tiering of responses, where the first response is to power cycle it. The second response is to switch off the reaction wheel and turn on another one that we might have as a spare. And then the other thing I have on my list here is watchdogs. One of the things that happens is there can be a single event upset, and that will cause a piece of spacecraft hardware to quit working, and we'll have some sort of what we call a watchdog timer that basically is looking at how long has it been since I heard from that star tracker. Gosh, it's supposed to talk to me 10 times a second, but I haven't heard from it for several seconds. I bet it's having a problem, and that will trigger us to do a reset of that. Sometimes that's actually built into the hardware itself. A star tracker might have an embedded computer in it that has its own little timer that it needs to reset, and the hardware inside the star tracker will say, I haven't heard from the processor in a long time. I'm going to go ahead and power cycle myself or reboot the software, embedded software in the star tracker. I talked already about safe mode. Here's an example of, the way some of this redundancy might be handled. Think of these compute elements, 2 redundant compute elements. Imagine each of those is an Arduino, and there's some interface electronics, which is like one of these Arduino backpack things. And it's we're using one of those to talk to each of these sensors. Well, you'd like to be able to use either of the computers with either of the backpacks, and so you start having to be able to crosswire these things, and that can start to get a little bit complicated. Gets a little bit more complicated when you have multiple pieces of hardware that need to have interfaces. This particular diagram is an example of what you would call block redundancy, where there's an interface electronics that has a set of the sun sensor and the star sensor out there. And if we have a problem with either of those, we would actually switch to the whole other group. So in this case, if the prime sun sensor craps out, I would switch to the backup interface electronics, and that would mean that I would switch both to the backup sun sensor and the backup star sensor. And you could imagine a thing where everything is cross-wired to everything else, but it gets super complicated when you do that. And all of those mechanisms to switch the signals to multiple places add some complexity and add more components that might fail. So there's always kind of this game we have to play with the complexity, and how do we have a fault protection system that's redundant, that typically, we build things to be redundant to any single hardware component failing, and we try where it's possible to be redundant to multiple things failing, or launching the spacecraft and having what we call a latent failure, where there's a failure in a piece of hardware that we didn't realize when we launched. But in general, we try to be single fault tolerant for the deep space missions, robotic missions that JPL builds. Human spaceflight has a much higher standard. Things there need to be triple redundant in a lot of cases. You need to be able to keep the crew safe even if there is multiple failures. And so as a result, the fault protection systems and the redundancy and stuff that you build into a human spaceflight vehicle, like what the SpaceX guys here are working on, the bar for that is much higher, and that comes with complexity, and that complexity comes with you got to think about how the systems are going to interact and stuff. I talked a little bit about block redundancy already. I briefly mentioned about the response tiers that you can, your responses can do different things depending on how many times you've seen a fault, or, you can respond, if you keep seeing the same problem, you can get more and more aggressive. And typically we walk down the set of response tiers, and first we start by power cycling a piece of hardware, and then we swap its electronics so that we're using a different set of electronics, and maybe swap to the backup sensor. And if we're still seeing the same problem, we might reset the flight software and reboot the flight computer, or switch to the redundant flight computer in case it's a problem with the flight software. I mean, obviously one of the more complicated pieces of a spacecraft is the flight software, and you can have an uninitialized variable floating around somewhere that incorrectly thinks there's a problem with the sensor. And a lot of times if you just reboot the flight software, that will clear that out. In some cases, the fault protection and the possibility of the fault protection doing something when it shouldn't, incorrectly thinking that there's a fault and swapping your hardware around, sometimes that's more dangerous than just trying to tough it out and play through. An example of that is, during the 7 minutes of entry, descent, and landing onto Mars, a lot's going on very quickly. It's a very high dynamic environment. There's not really quite enough time to switch to the backup computer, or doing so is very dangerous. And so in that sort of circumstance, a lot of the fault protection gets put into what we call a battle short mode. And that term comes from old Navy use on submarines, where they would replace the fuses that they had with bars, brass bar that they knew, because they didn't want, if you're in battle, the fuse to blow. Sure, it would protect your hardware, but we're trying to escape from the people that are depth charging us, so it's more important to just use every bit of contingency. So we typically will put the fault protection into a battle short mode if we're doing a critical event. We're trying to get in orbit around Jupiter. We don't want the maneuver as we're trying to get in orbit around Jupiter to stop midway. We want it to try and press on if it possibly can. So I just said that we don't really have time to switch processors during EDL. We actually cheated a little bit on that for Curiosity. We had this thing, this software that we called Second Chance, which ran in the backup computer, and under certain conditions, it could seize control from the main computer if it thought was very convinced that the main computer was having a problem. It would seize control and try and do the landing. And a comparable thing happens. The Soyuz spacecraft has a crazy high G ballistic entry mode that if it thinks things aren't going right, can kind of switch over. And we sort of had that for the Mars landing as well. Let's see. Okay. Testing. Testing is super important. We test the living shit out of everything. Here's me using a precision calibrated Harbor Freight lamp to test a sun sensor, which you see there with the little slot on it hanging out the side of our cruise stage. We were actually testing for the phasing of it, that we had the thing mounted on there correctly and all of the wiring was correct and the flight software knew which way was up. And basically what we would do is move that light around and say, oh, I moved it to the left. Does the flight software believe that? We do testing on the actual flight hardware. We do testing on a test bed where we have the engineering models of the flight computer and the sensors, laid out on a benchtop, and have a simulation that is feeding them data as though they're flying in space. We do a lot of our flight software testing in that venue. And, the testing that we actually do on the real spacecraft is mostly to verify that we actually have the connectors mated properly, all the wires are working, the real flight hardware is working. We don't do much. We hope we don't end up testing the flight software and its behavior much when we get actually out on the floor building the real spacecraft. And as much as possible, we try to test things as we're going to fly them. If, some of those things are very hard, like Mars landing is hard to get to the real conditions of the Mars lander in velocity and altitude and density, and Mars gravity is different than Earth gravity. And so, a lot of things have to be done in simulation, but as much as we can, we test as they're actually going to be flown. You see us there as part of our test procedure. You can see the Curiosity descent stage with its radar down there, and the standards for doing our testing are very high. So how do we figure out what went wrong? We have a bunch of different kinds of telemetry that we get from spacecraft. The flight software has a lot of what we call telemetry points, numbers and messages and stuff that it puts out so we can tell exactly what's going on. The EHA kind of telemetry are things like temperatures and velocities and how fast we're turning and how strong, what are the accelerometers telling us. Those are numbers that you might plot versus time. We also have these things that we call EVRs. They're more for things that are like events. They're more like you would put a printf in your code to see when you got into this block of software. And so we use those to verify that the spacecraft has changed modes like we expect it to or commanded it to. We also have the possibility of generating telemetry that is larger chunk of data that might be an image or a whole series of measurements over a period of time that we call data products. And then we have lower level things like that we call tones. During the actual Mars entry, you don't really have enough telemetry bandwidth to get even 10 bits per second. And so we instead do a thing where we just modulate the subcarrier frequency of the radio signal. So, and you can detect those changes at a much more, with much less signal. You can detect those changes with much less signal than you can get actual telemetry. And we use those for things like we've released the parachute. We're separating the heat shield off of the bottom of the rover and stuff like that. And you detect those with tones. And we started to use that, years ago. We lost a couple of spacecraft and we didn't really have any information about what happened when we lost them because we had the radios turned off. And so this is a way that we can get information that the spacecraft is doing what we expect and has gotten to a certain part in a critical event like entry, Mars entry, without actually having telemetry. Let's see, audit trails, autopsy reports. If the flight software crashes, your Mac, when it crashes, it puts up a thing and says, hey, you want us to send Apple all this crap about what just happened? Well, we have those on the spacecraft as well. It's a little trickier when you have a prime and a backup computer because, your prime computer just crapped out. You want to make sure that you can get that information over to the backup computer, which may have taken over, so that you can debug what happened on the primary computer. one of the advantages, debugging our stuff when in space is just like debugging your Arduino project. You scratch your head a lot. We have the advantage of knowing a lot about the hardware. It's gone through a very rigorous test program, and we have, lots of data that we've taken from the sensors and actuators and the flight software before we go. So we have a real deep understanding of how the hardware works, and if we have a problem with a piece of hardware, we can go back to the people that built it, the people that designed it, sometimes companies outside of JPL, oftentimes that, to bring experts in and say, explain to us exactly how your thing is supposed to work and what you expect, and so that helps a lot if we have a problem. We have test beds, which are these, tabletop with the engineering hardware spread out on them, that with a simulation that we can use to try and duplicate what just happened on the spacecraft and step through it moment by moment very carefully, sometimes with a much higher data rate of telemetry, so that we can, if we can duplicate what happened on the spacecraft, then we can, figure out exactly, oh, well, here's this line of flight software code that was causing that. Talked a little bit about, the various, test beds with different levels of hardware. We also do, in early flight software testing, we'll have all complete software simulations of the spacecraft that includes running the flight software in some sort of an emulator and a simulation that simulates the environment. One of the most useful things, in the space debugging spacecraft problems is the power of time correlation, being able to look at a plot of telemetry and seeing things that happened at about the same time very often leads you to the cause of things. The star tracker just suddenly dropped lock. I don't know, we were just minding our own business and the star tracker quit working. Why is that? Oh gosh, that is about the same time we would have, expected a solar flare to arrive at the spacecraft based on the information I see here on, spaceweather.com. And being able to correlate those things, well, okay, is what we saw consistent with a solar flare whacking our star sensor with a bunch of protons, or was it really a hardware failure with the star tracker? Let's see. Yeah, so here's an example of some, engineering telemetry. The data rates of this stuff might be as high as 10 samples per second, might be just 1 sample per minute, depending on, how dynamic the telemetry for that particular thing is. This is part of the, Deep Space One telemetry for its attitude control system of how much pointing error is there, and so we got it pretty fast. Temperatures, things that naturally change slowly, we might only get one sample every few minutes. Let's see, we do a lot of work before we launch and even during flight, getting ready for something like entry, descent, and landing on contingency procedures, being, ready for certain things to happen and knowing in advance what we're going to do to respond to those. In robotic space flight, oftentimes those plans don't get used exactly because we almost never see exactly the problem that we anticipated, but they're really good practice to go develop those procedures anyway. In human space flight, it's much more common to have an exhaustive, every possible light that could come on the control panel, we're going to respond to it in a particular way, and we're going to follow everything by the book. So, there's a little bit of a cultural difference between the robotic exploration because of the different levels of risk there. But, in the case of something like Apollo 13, you're going to have to improvise because this thing that just happened is not on your list of, things that you can pull off the shelf a response for. If we see a problem, we can swap the hardware. We can, sometimes we'll see something like, oh, I think this reaction wheel on the spacecraft is starting to go bad. Let's shut that off and tell the flight software we're not going to use it anymore. And we'll give up the redundancy, but we'll save the lifetime on that wheel by not continuing to operate it all the way to failure as its bearings, reach their end of life. A lot of times we'll have commands in the flight software that are backdoor commands, that are things that we use when we're testing and stuff like that. And a lot of times you need to bring those out when you have a problem on the spacecraft and apply them to a specific circumstance that you get approval from the project manager that we're going to use this thing that we told you before launch that we were only going to use in test, but we really need to do it right now. And he'll say, okay, go in the test bed and make sure the thing you're going to do is not dangerous. And we'll go, okay, and we'll test it. Pretty much the only thing you can fix on a spacecraft is the software, a robotic spacecraft. Human spacecraft, I guess the guys can go out and hammer on things, but on a deep space, something going to Mars or Jupiter, software is the thing you're going to have to fix, even if it's a hardware problem. And so a lot of the times what we end up doing is working around hardware problems somehow in the software to keep the mission going. Like as I mentioned before, functional redundancy saves your ass a lot of the time. So let me see if I can blast through a few of these examples. Here's the Spirit rover. The high gain antenna is right here. The low gain antenna is the aluminum mast thing there. We use the high gain antenna to get commands up to the spacecraft, send telemetry down. In order to point that thing at the Earth, you need to know how the rover is parked on the Earth, how much tilt there is, what heading it's parked at. And so we have a system, an attitude control system, an attitude determination system on the rovers, and we have the same sort of thing on Curiosity to enable us to point the high gain antenna at the Earth. So one morning, shortly after the Spirit landing, the spacecraft was programmed to wake up and point its high gain antenna at the Earth to have this comm session, and it didn't happen. And we got some telemetry at a very low rate later on from the low gain antenna, and it said what happened was I tried to move the high gain antenna, but it was like taking really a lot of current, and so my fault protection detected that, and to protect the mechanism, shut off the motors to the high gain antenna. And we're like, oh shit, that's not good. If that's a failure of the bearing or something like that, that'll mean we can't use the high gain antenna, and that would be very bad. Here's another shot of it. You can sort of see the high gain antenna a little better there, and the camera mast there sticking up out of the middle of the deck. Here's some engineers that are working on trying to figure out how to get Spirit unstuck. It, at the end of its life, got high-centered on a rock in this very, very fine soil, which they've set up a test in our test bed to try and experiment with ways to figure out how to get it unstuck. And though they tried valiantly for many months to do that, they were not able to get it unstuck. So that problem that we had with the high gain antenna turned out to be this. You'll notice that the mast, the camera mast, which is sticking up, there's a little black star sort of at the top of the screen there. The camera mast is actually making a shadow which falls across the top of the spacecraft. And this isn't the exact day that this happened, but what happened on that morning was that that shadow of the camera mast was falling on the high gain antenna gimbal that points it. And so it was a lot colder than it usually was. Usually sun comes up in the morning and starts warming the stuff up on the deck. And so it was really cold, the lubricants were really stiff, and so it took a lot more current, and we had very conservative numbers there for how much current it would allow. And so it said, oh, I'm going to protect myself. And so once we figured that out, we adopted a rule that we're going to always park the rover so that it doesn't do that. And there's some other reasons why they control how they park the rover now. But it turned out to be not that big a deal. But Another war story, I worked on a project called Deep Space One, which was a first planetary mission to use an ion engine. It was, the technology development for this project called Dawn that is now in orbit around Ceres after having visited Vesta and done a whole mapping campaign there. And so Deep Space One was done as a very inexpensive program to validate some technology. And so it had very little redundancy. It had very little hardware redundancy. It had only a single star tracker. Its primary mission, we launched it from the Earth. The dark colored arcs are places where we were thrusting with the ion engine. The dashed things we were coasting. We did a flyby of an asteroid that was, partially successful. We learned some things from doing that. And then, after that flyby, we went back to NASA and said, hey, we think we can fly it to a comet out here and take pictures of that. Will you pay us to do that? And they said, yeah, that sounds great. And shortly after that, they gave us approval to do that. The star tracker on the spacecraft failed. And, we think in retrospect it was probably a DC to DC converter or something, and it went bad. And we really, really needed to have a star sensor in order to do our comet flyby. It's the thing that tells the spacecraft what direction it's pointed, and we need to be able to know that and control that in order to communicate with the Earth, in order to thrust in the right direction to fly ourselves to this comet that we're trying to fly by. And so that was pretty bad. But before we launched, I had lunch, or dinner, I guess it was, with a friend of mine. We were sitting at a pizza joint, and we were saying, hey, what could go wrong? The solar arrays could not deploy, and maybe this actuator wouldn't work. And one of the things we talked about is, what are we going to do if the star tracker craps out? And we said, we have a science camera on board the spacecraft. Maybe we could take pictures of stars with the science camera and use that somehow, And this, we were just bullshitting, to kind of calm our nerves before launch. And so, when the star tracker failure happened, we remembered that conversation and let's look and see if that's really possible. Now, it was a little challenging because it turned out our science camera was kind of funky. Science camera had it was sort of a combination instrument that was both a camera and an infrared spectrometer. And in order to combine those functions, it had a hole in the side of it with some other mirrors and stuff that was used for the infrared sensor. And it turned out that sunlight could go in that hole and bounce around and put these, crazy sun glint things on the camera. So the camera was sort of an unpleasant thing to deal with, but it would sort of take pictures of stars. So basically what we did is we wrote a bunch of software, to lock on. Well, the other major difference is that the star tracker has a wide-angle lens on it, so it can see a whole bunch of stars. And this thing is a telephoto thing that's designed to take pictures of asteroids and comets from a great distance. And so basically you can only get one bright star in it or two at a time. And so we went and devised a bunch of software that would lock the camera on the one star and basically say, hold that star in the center of the field of view of the camera. And we, used that to continue the mission. We figured out some tricks to do with the camera, like we subtracted we took some pictures with the camera just of black sky, and then we subtracted the image, which got rid of a lot of that stray light problem that we were seeing. And then we would take multiple pictures and add them all up together. This is an example of us taking pictures of the comet on our way to was our target with that background subtraction and stuff done. There's a whole story here that we probably don't have time to go into, that it was very tricky to get the spacecraft working well enough without the star tracker in order to upload this new software that we had written to it. We had to do a bunch of tricks to to make that happen. And luckily, there was enough features in the flight software that we were able to do that. This is the moment where I'm going to ask Brian, do you want me to keep going? Do you want to show our video and get on to the next thing? I've got one more, he says keep going. Okay. I've got one more kind of war story to tell you, and then we'll decide if we want to show the little video. So I think I said all of that. Yeah, we had to hack our way out of safe mode in order to get that flight software patch. Basically, when we're in safe mode, like I said, we have to use a low gain antenna, which only has a very low data rate capability, and it would have taken months for us to upload the flight software patches that we needed with that. And so we jury-rigged away without having the star tracker to point the high gain antenna at the Earth so that we could have high rate comm, though we had to sit there and basically say, oh, we're drifting to the left, send a command to, point us back at the Earth. And it was very exciting. But it worked. We got a picture of a chicken leg. You probably missed it in the news because the flyby of Comet Borrelly happened about 1 week after 9/11. So you can imagine our state of mind during that week was a little challenged. And of course, getting it in the press was not an option. But it was successful. The flyby was successful, and we got it done using, just that crazy, using the science camera locked on a single star, both for thrusting and doing the science observations. So the final war story I wanted to tell you was about flying Curiosity to Mars. This is a relatively unknown aspect of the whole Curiosity story, so don't tell anyone, it's a secret. But the RCE is the rover compute element. It's the flight computer. It controls the rover. It sits down in the rover. But it's also used to control the descent stage during entry, descent, and landing, and control the whole spacecraft as we're flying it to Mars. It is redundant. There's 2 of them on there. And so here's sort of how the pieces go together. Heat shield at the bottom, the rover with its wheels folded up, the descent stage, and a back shell that has a parachute in it. And the thing at the top, number 1, is the cruise stage, which I was sort of most intimately involved with, which is got some solar panels on it, some thrusters, some fuel tanks, and it's the spacecraft part that flies the rest of this mess to Mars and dumps it at the top of the atmosphere in a very precisely controlled time and velocity and position. There's a picture of the cruise stage. You can see some fuel tanks. The things with red guards on them on either side are our thrusters. There's an electronics box there. There's no real computers or brain much in this. There's basically an Arduino backpack thing in there that's interface electronics, CNDH, but the flight computers are all down in the rover. And there's how we fly to Mars. The thing is spin stabilized as we fly to Mars. It spins at about 2 RPM, which is about this fast. But with the thing the size it is, that's plenty of gyroscopic stability. And it has harking back to the discussion of the lighthouse. We had a couple of mentions by speakers today about the lighthouse and a V-slit version of the lighthouse system. Well, the star scanner on Curiosity is a V-slit star scanner that works basically the same way. As it spins, it has this little V-slit, and as the V-slit crosses over a star, it goes blink, blink, and the timing of those times when the star transits the V-slits is measured very precisely, just like the lighthouse stuff is done, and used to determine the orientation of the spacecraft. And then when we get to Mars, we dump the cruise stage off of there, and just the entry vehicle goes and hits the surface of Mars. Let me back up one slide. and spin stabilized. Yeah, I just want to make a couple more points here. One is, it's important that we know how the spacecraft is oriented and that VSLIT star scanner thing is working. We use that, we need to keep the solar arrays pointed at the sun. We go, about halfway around the sun between Earth and Mars, and so we need to move the spin axis of this thing around by about 180 degrees during the flight to keep it pointed at the sun, to keep the solar panels pointed at the sun, and keep the antennas pointed near the Earth so we can have communications. And we also have this set of thrusters that we use to horse the spacecraft around like that are also used to correct the trajectory on the way to Mars. We typically, launch the spacecraft at Mars with a little bit of an offset so that we know if the spacecraft is dead right from the outset, it's not going to run into Mars for planetary protection reasons. And so there's a correction that has to be made to make us go to Mars. And also we make a successive set, usually 4 or 5 corrections to the trajectory on the way to Mars so that we, can hit this kind of football field sized target at the top of Mars' atmosphere at just the right time. And so we need the spacecraft to know its attitude in order to do that. That process of using the star scanner to do that is called celestial mode, and we had a little problem with celestial mode. I talked about the rover compute element. It's a RAD 750 processor. Stabilized injection errors, planetary protection offset. Yep, covered all that. So celestial attitude determination, I talked about a little bit about how that worked. So here's us on our way to Mars. There's the orbit. Like I said, we go about 180 degrees around. A week or two after launch, we were supposed to do our first trajectory correction. And just a few days after launch, we activated this star sensor and the celestial mode software that's supposed to tell us how the spacecraft is oriented. Everything worked fine. The celestial software started working, and then we said, "Hooray! That's now we're ready on our way to Mars." And my team and I went out to have lunch. We went to a Japanese restaurant, ate some sushi, and just about the time we were finishing up, our cell phones all rang, and they said the spacecraft is in safe mode. There are EVRs, there are those little printfs out of the flight software that says that your software crapped out. And so why don't you come back right away? And so we went back and started, trying to figure out what the heck happened. And we looked at all of our telemetry. About an hour after we went into celestial mode, we had this problem. The initial suspect was our software because we had just turned it on, and it seemed like it was having a memory fault at addresses that pertain to us. We need that celestial mode to work in order to do our trajectory corrections and do the turns and stuff we needed to do. And for a while, we were sort of under the gun that it was us, but as we started to dig deeper into it and do an investigation, it turned out that the problem wasn't really our fault. It was actually a problem with the flight computer, and that it was corrupting the instructions as it was pulling them out of memory. Only very rarely, and only like for certain addresses, which happen to be addresses used, the range of addresses where our celestial mode software was sitting. We eventually, I can talk about that more in a second, but here's this. Yeah, foolproof and incapable of error. We were super lucky that there was a workaround for this. The actual problem was with the memory management unit that's built into the processor, and we did a bunch of tests in the test bed where we hammered this one set of 2 minutes, okay. We hammered this one set of addresses, you know, a jillion times a second, and eventually came to the conclusion that these, you know, the memory was being corrupted, and we realized that the problem existed on both of the computers. And if that problem happened during entry, descent, and landing, it would kill us dead. It would, you know, likely mean that we would crash. And so that was a big concern of us, but an even bigger concern, more immediate concern, was we needed the celestial mode software to do that first trajectory correction and get us going back to Mars. And so luckily we had enough functional redundancy that we could keep flying. We had a mode that was built into the flight software from the very beginning called pseudo-celestial, which basically said, do everything that you're going to do in celestial mode, but don't worry about the fact that you're not getting any VSLIT star sensor measurements. You know, we'll tell you ahead of time where we think the spacecraft is pointed, and you just play along and act like everything's okay. Use just the data from the sun sensor, and you know, and that mode turned out worked for us to do trajectory corrections. We could do turns, not with full accuracy because we weren't really measuring anything. We're sort of dead reckoning when we did turns. But we accomplished that first crucial TCM. We did the first turn that we needed to do to make sure that we kept getting power on the rays. And that bought us time to figure out what the heck to do about this computer problem. Eventually, it turned out that they could reprogram the memory manage unit of the processor in flight, because when we boot up the processor, it goes and gets some parameters for that and sets it. And the folks that built the flight computer, you know, eventually figured out, okay, set these parameters, delay a little bit longer when you set up the memory addresses before you pull the instructions out. And that allowed us, we flew the rest of the mission with that. Here's a final shot. This is actually from Spirit. You see our tracks. There's a dust devil out in the distance there that's kind of cool. Do you want to take 3 minutes to show that or play on? He put his thumb up.
You doing it?
Yep. I think he looked and saw what this was.
Okay.
So this is...
Thanks.
Thanks, boss.
Okay.
So this is our landing. This is the Curiosity landing.
We will control our attitude on shoot. We are decelerating.
This is basically the audio that we're hearing in the control room.
And descending, we are at 150 meters per second.
And the pictures from the landing
Dynamic
camera.
phase. Come back again with wrist mode dynamics.
Wrist mode is nominal.
We are 9 kilometers and descending.
Leads active. Valid range.
Net filter converged with a velocity correction of 0.7 meters a second.
We've acquired the ground with the radar.
An altitude of 8 kilometers.
Speed shield has separated. We've found the ground.
Expand tones due to earth occultation as expected.
We're standing by to prime the Anomaly engines in preparation for powered flight. We're down to 90 meters per second at an altitude of 6.5 kilometers and descending.
When things get smooth is when we come off the parachute.
Flight EDL, we got some Tweedo warnings.
That was scary.
It is in battle short mode, so it should power through them.
Direct to Earth communications at this time. We may have lost it already. We're down to 86 meters per second at an altitude of 4 kilometers and descending. We've lost tones from Earth at this time. This is expected. We're continuing on Odyssey telemetry.
Ground solution equals minus 10.8 meters, vertical velocity of minus 82.8
We are priming. Power
meters per
descent logic
second.
start enabled. Standing by for batch shell separation.
Signal to Odyssey is still strong.
We are in powered flight. We're at an altitude of 1 kilometer descending, about 70 meters per second.
Signal to Odyssey
Control
remains
error.
Down to 50 meters per second. 500 meters in altitude.
You'll see the wheel drop into view.
Standing by for sky crane.
Constant velocity accordion nominal. Altitude error 5.9 meters.
We found a nice flat place. We're coming in ready for sky crane. Down to 10 meters per second. 40 meters altitude. Sky crane has started. Descending at about 0.75 meters per second as expected. Expecting bridle cut shortly.
Signal velocity remains strong.
Tango Delta nominal.
Yep. UVL comm configured.
Review stable.
UHF telemetry.
Review stable.
UHF is good.
Touchdown confirmed. We're safe on live.
Cool. Well, thank you very much. I'll turn this back over to Brian for the next event. Yeah, they have a thing.
Yeah, okay.
Thank you.